The goal of this video is to help you follow the development of what we call a compound angle formula. And following that, you'll also be asked to develop um, a compound angle formula by following this example, and then later on you'll also be asked to use them. So as we go through this video, feel free to pause and rewind, review, and also to take notes on the template that was provided in class. So let's begin with the definition of compound angle. It is an angle that is created by adding or subtracting two or more angles. Over here to the right, what we're going to do is try to determine the cosine of the compound angle A minus B. In fact, as you'll see, as this proof is developed, that the cosine of A minus B is actually dependent upon both the sine and cosine of angles A and B. So what we'll do is begin our proof by setting up the angle A minus B using the unit circle. Notice here that the angle in green, that is acute angle B, is inside of this right angled triangle. The coordinates of this point on the circumference of the circle are none other than cos B, sine B. If we then determine the placement of another point, let's call this a point that is drawn by rotating through an angle of A, would have coordinates cos A and sine A. It then follows that the angle formed here, that is subtended by an arc between these 2 points, is A minus B. So our proof is as follows. Cosine of A minus B is equal to sine A sine B plus cos A cos B. So this is an identity, and it is up to us to use a geometric form of reasoning, that is through the diagram, along with some algebra to come up with it. So the first thing we'll do is consider the distance that is between these 2 points by using a distance formula as follows. So recall that distance between 2 points is the square root of the sums of the squares of the differences of your x values and y values. By squaring both sides, we'll remove the radical and we'll have an expression for d squared. Okay, so moving forward, imagine what might happen next. Let's give consideration to finding the length of this side, that is side C, with respect to cosines and sines. Before moving forward, this is not provided in the template, but just to give you an idea or another representation of the diagram that might make things look more familiar to you. If we were to take that same angle and rotate it as such, okay, this does provide a visual representation of the angle A minus B, which you can see right here. So our task, of course, through this proof is to determine an identity for the cosine Actually, that's not working out very well. Let's type that into place instead. So our job is to determine identity for cos A minus B, which is the x-coordinate of this point I've now placed in blue, along with the y-coordinate. So you will also, later on, determine an identity for sine of A minus B, which is the y value of this particular coordinate. So moving along with our proof, let's do the following. The diagram had D as our C. Let's call x1 cos B, x2 cos A. y1 will be sine B, and y2 is sine A. Now because of that, we'll just do a substitution. So where we get x's and y's, we will put in the corresponding coses and sines. Now following the mathematics that we already know, we can use these squares to expand those binomials. And if we do so and tidy things up, we will end up with the following. Okay, so I took another step here just to show you that the square does indicate this, that there are two of each factor. And it's useful to do that as a reminder that there will be two cos A cos B's. Same thing was done over here with sine A minus sine B. And upon squaring, do recall that there is a middle term, minus 2 sine A sine B. If we rearrange this a little bit to group terms more conveniently, consider this. Note how the squares of the quadratic trig ratios have been grouped together. And over here, these linear terms, or linear trig ratios, have been grouped together. This grouping has been done conveniently for us because of the known fact, and this was established in 3U math, that the square of sine theta plus the square of cos theta is equal to 1. And because of that identity, it allows us to replace a number of terms such that we end up with the following. So you can see the two ones come from both sine squared A plus cos squared A, and the other one from sine squared B plus cos squared B. Simplifying this, we end up with the following statement, which we'll label as equation 1. Now, being that this is being labeled equation 1, generally speaking, when your teachers did that, it was a prompt that you would be searching for a second equation so that you could solve a system of equations. So this important fact here, not that you need to write it down, but definitely read it and consider it. So if we had a second equation describing c squared explicitly, that means another c squared equals equation. We would set the first and second equations equal to each other, and we would no longer have a c term. We would simply have cos A's and B's. So the other c squared equals equation, just what exactly is it? Well, let's think of it this way. Let's consider the triangle that was presented earlier, with a contained angle A minus B and a side opposing that, side C. Recall that in whether it be right triangles or non-right triangles, we had two other formulas that could apply. We had both the sine law and the cosine law. In this case, what we're going to do is use the cosine law in this situation because we want to find the length of a side opposing the contained angle. Recall the sine law was stated as follows. Notice that I have moved away from using the same lettering systems of A, B, and C, given that those values have already been used to represent angles in the diagram. Now E and F are both radii. That means that these two side lengths here of unit length 1 represent the radii of the circle. They also represent the sides adjacent to the contained angle, which is A minus B. So with that in mind, we can replace both E and F by 1's. Angle D will be the contained angle, A minus B, and D, the distance between these 2 points, will be length C. So we end up with the following. Simplifying even further, we come up with equation 2. Now consider what we can do with both equations 1 and 2. Do notice that we do have cos A minus B. This is what we need to have either on the left or the right hand side of our identity. So let's set them equal to each other. We have equations 1 and 2. If we substitute, we end up with the following. Notice now that we can rearrange this and eliminate a term. The 2's we'll subtract out. Also notice that negative 2 can be factored from the left side and then divided out entirely from the equation, dividing both sides by minus 2. And in doing so, we end up with the formula that was given to us at the onset of this video. So as you move forward with the lesson today, you will be asked to determine an identity for the cosine of A plus B. A particular hint will be provided to get you going on that. Moreover, and further to this, you'll also be asked to determine an identity for the sine of A minus B. Again, another hint will be provided to get you going in the right direction.